Okay, so today we are going to start chapter 14, which is our chapter on acids and bases. And we're just really today going to look at sections 1 and 2 and 11. And a lot of it is just definitions, but I felt like we should probably review all of those since this is where we would have been last year during our remote time. Okay, so we're going to spend a lot of time looking at particle models today. So when I look at this particle model, I can see that I have molecules of acetic acid. I can see that I have acetate ions. And most importantly, I can see that I have a hydrogen ion. And the fact that this solution breaks apart to give me a hydrogen ion tells me that this is an acid. Now, there are several definitions of an acid. One definition would be the Arrhenius definition. And basically, the Arrhenius definition says that it's a substance that produces hydrogen ions. So that would be one way to define this. And the way we prove that something is an acid or a base is by writing its dissociation equation. So you would start out with the molecular ionic compound. So I have CH3COOH. It's going to break apart. And we already talked about that this produces an acetate ion. And it also produces a hydrogen ion. So that would be the way that I can prove that this is an acid. Another way to define acetic acid, which is the component that we have in vinegar, is we can also describe this as being a monoprotic acid. And when I say it's monoprotic, mono we should know means one. And this means proton. So in acid-base chemistry, when we talk about a proton, we're really referring to the hydrogen ion here. Because if I have a hydrogen ion, hydrogen atom has no neutrons. And then the ion means it's given up its one electron. So the only thing there is that proton. And typically in front of the hydrogen ion, we put the word acidic. So it has one acidic hydrogen. Now, acids can not only be defined by how many acidic hydrogens it has, it can also be described by if it's strong or weak. And in this case, this is a weak acid. And the definition of a weak acid is that it does not just completely dissociate. And I can see that from my particle drawing. The fact that this drawing has molecules and ions is the evidence that this is weak. In weak acids, the equilibrium lies to the left. Which means that it produces very few product, in this case, very few ions in solution. And the another characteristic of being weak is that this is going to have a small Ka value. Okay. So we know K is a symbol for equilibrium constant, and when we're talking about acids, we call it a Ka value. Now, another way to define an acid besides the Arrhenius definition is the Bronsted-Lowry definition. And the way that it's defined here is that it's a proton donor. So in other words, it has a hydrogen to give away. And again, we can write an equation to prove that this would be a proton donor. All right, so again, we would have our molecule CH3COOH. Now in this case, we're going to show that it's reacting with water. Okay. Now, when we write equations and something's a weak acid or base, notice that the equations have a double-sided arrow, which means it's reversible. And so here's that one acidic hydrogen. It's going to give it away. So we're left with CH3COOH. The H breaks off. And so that's how I went up with an acetate ion and a hydrogen ion. And that hydrogen ion attaches to water. So this actually becomes H3O+, which we know is the hydronium ion from acid-base chemistry. Okay, now we should talk probably a little bit about water. Water is an amphoteric species. And this means it has the ability to act as an acid or base. Okay, and then the other characteristic we can talk about, so if that's true, remember that my CH3COOH has the acidic hydrogen, so that makes it an acid. So that means that water has to be the base. And then on the product side, we make conjugate acids and bases. So an acid, when it gives up a hydrogen, it forms a conjugate base. And when a base gains a hydrogen, it forms a conjugate acid. So you may see the term conjugate acid-base pairs. So for example, the acetate ion and the CH3COOH molecule, acetic acid molecule, would be one pair, and then water and the hydronium ion would be another pair. Okay, all right, so that's our first one to look at along with all of its definitions. Let's look at our next species. So again, we want to look at the particle model, and in this case, I see a hydrogen ion, so that tells me this is an acid. And again, I can prove that it's an acid a couple of ways. We can write a dissociation equation. So I can show that this breaks apart into a hydrogen ion and a nitrate ion. So this would be a representative of my Arrhenius definition. And I can also show that this reacts with water. Okay. So again, the acid gives up a hydrogen. So we're left with the nitrate ion. And that hydrogen ion attaches to water to form hydronium. And so this would be demonstrating the Bronsted-Lowry definition of an acid. Now, this species is going to be a strong acid. And so again, the way I recognize that is that if I look at my particle diagram, there are only ions in solution. So strong acids completely dissociate. And notice that they're going to have an arrow that points in only one direction in their equation. So in this case, the equilibrium is going to lie to the right. So this tells us that only ions are going to form in solution. And these have really large Ka values. So actually they're so large we don't even list Ka values for these because they only make product. Okay, and then obviously not everything's going to be a particle model on tests and quizzes for acids and bases. So on your periodic table that I gave you at the start of the year, there should be a list of all the strong acids. I would suggest that you memorize that list. Okay. All right, let's look at our next picture. So my next picture, if I look here, the ion that we're producing here is the OH ion. And so that's telling me that this is a base. And just like when we talked about acids, we can talk about the Arrhenius definition of a base. And this is a species that produces hydroxide ions. And again, we can write equations to prove that it's a base. Now, in this case, this is ionic compound. So the only type of equation that we can write here is a dissociation equation. All right, now just like with acids, bases can be classified as being strong or weak. And if I'm looking at my diagram here, I can see that the only thing in solution is ions. So this tells me this is a strong base. Now, obviously, we're not always going to have particle drawings. So how do we recognize a strong base? Because there's no list here. You are looking for a group 1 or 2 ion. And that ion is going to be combined with the hydroxide ion. So again, if it completely dissociates, the equilibrium is going to lie far to the right. So telling me that we're only producing ions in solution. Okay. And again, such a strong base will not have a K value for us to look at. All right, let's look at our next particle drawing. So in this particle drawing, I see molecules of NH3, I see ammonium ions, and I see hydroxide ions. Now this hydroxide ion is telling me that this is a base. And in this case, when I look at the molecule, it's NH3, there's no hydroxide ion. So the only way to prove that this is a base is to show that it's reacting with water. Okay. Now, in this case, if ammonia is the base, water has to be the acid. So it's going to give up a hydrogen. And you're left with the OH in your water molecule. So again, this is my base. This is my acid. A base gains a hydrogen to make a conjugate acid. And an acid loses a hydrogen to become a conjugate base. Now we talked about the Arrhenius definition. There's also a Bronsted-Lowry definition. And that's the one we would have just looked at in this equation. And in this case, the base is going to be a proton acceptor. All right, and the fact that I have the molecule and the ions, this tells me this is a weak base. And just like with an acid, it means it does not completely dissociate. So the equilibrium is going to lie to the left. And this also has a K value. And if it's lying towards the reactants, it's going to be a small K value. And we call these KB. The B, of course, recognizing that this is a base. Okay, so we've talked about the Arrhenius definition. We've talked about the Bronsted-Lowry definition. So there's one more acid-base definition we talk about, and that is the Lewis definition. So for something to be called a Lewis acid, its definition would be that it is an electron pair acceptor. And to be called a Lewis base, you have to be an electron pair donor. Okay, so the best way to be able to recognize this is to be able to draw Lewis structures. So I have this, and it's going to react with water. And we are going to make all right. Now, the fact that this water molecules have electron pairs that can donate makes this the base. So obviously SO3 becomes my acid. And the substance we've made here at the end is actually H2SO4. And we would define this as a diprotic acid. The di, of course, meaning that it has two hydrogens, acidic hydrogens. So here are the two. The other way we can define this is as an oxyacid, and I'm going to save that definition for later when we get to the sections at the end. Okay, and then we have a little problem we're going to look at. So I'm going to give you some substances. Okay, and what we're going to do is we're going to list these from the strongest to the weakest base. And so the rule we're going to use to figure this out is that if I look at these, everything that's an anion here with a negative charge, it is the conjugate base of a weak acid. So the thing we want to recognize is that the weaker the acid, the stronger its conjugate base is going to be. Okay. All right, so we want to first of all recognize that we have water. The second species we want to recognize is this chloride ion because this is the conjugate base of a strong acid. And that's important because strong acids are not going to have a Ka value. Okay, then the rest of these, the acid should be listed. Okay, so NO2 would come from nitrous acid, Fluorine would come from HF. And CN would come from hydrocyanic acid. And these are their Ka values. Okay, so if what I said is true, weaker the acid, the stronger the conjugate base, we want to start with this list of Ka values. And the weakest acid on this list is HCN. So that tells me that the strongest conjugate base would be the cyanide ion. The next on the list is HNO2, so the nitrite ion. And then the next on at the top of that list is HF, would be the fluoride ion. Okay. All right, so water would come next because it's in between those weak acids and strong bases, or weak acids and strong acids, sorry. And so then the chloride ion would go last. Okay, so I would give you the table of Ka values so that you have it. You're not going to need to memorize Ka values.